Okay, so I'm going to do now an example with triple integrals, and you'll see that it is the same idea as the example for double integrals, but it's a little bit more tedious because there are more possibilities that you could include or consider. So let me do this concretely. Say that you want to find this triple integral of the function x, y, z dv, where r, so again, the point is that this is like a function w of 3 variables. So the graph, in order to draw the graph, you would need really like a fourth axis, which is perpendicular to the other 3 that we have in space, but we cannot find that. So we don't try to look at the graph of the function itself. So we don't have like the domain viewpoint and the graph viewpoint from before. I mean, we only have the domain viewpoint. So from the domain is being represented by this region R. And the idea is that, say I want the region to be, just to make things easy, I want the region to be like a cube. So I'll integrate from say 0 to 1, 0 to 2, 0 to 3. Okay? So R is a cube. Well, not really a cube because the 3 sides would have to be the same, like a parallelepiped. So it's from x between 0 and 1, y between 0 and 2, and z between 0 and 3. Okay? The point is that in order to do this triple integral, you can do the same as before. The basic idea is to replace dv well, so now dv, again, dv is like a little piece of volume that you see here. So the question is, in how many different ways you can write this little piece of volume? Well, basically, there are 6 different ways. Right, you could say that dv is dc dy dx. You could say that dv is dc dx dy. You could also say that dv is dy dc dx, or dy dx dc, and you could also say that this is dx dy dz, or dx dz dy. Okay, so there are 6 possibilities. And so in principle, what I'm trying to say is that you could slice this up in 6 different ways. Just to illustrate why there are so many different choices, like you could slice up first by fixing a value of x. Okay? And then when you fix the value of x, later you have 2 more choices, which is whether or not you slice this rectangle. Well, I mean, you're going to let the value for x vary, but then z can change here, right, and y can change. So you could do slices which go this way or which go this way. And so that gives you 2. So there are 2 ways to cut down these sheets that you get. And so since there are 3 original variables or axes you could have started with, it gives you 2 plus 2 plus 2, which is 6. And so the point here is that we can find this same integral in 6 different ways. I won't do the 6 ways because it would take forever. I will just do 2, but I will write it in all possibilities so that you see what are the differences. So So again, the idea is that x, y, z is a function that never changes. And now the only thing that's changing is what you're replacing dB with. And so again, we have 6 options. Let me write them here and move this on the other side. So this is dc dy dx, dc dx dy, dy dc dx, dy dx dc, dx dy dc, dx dz dy. And again, in each of these potential different integrals, you go from the inside to the outside. So in here, the first thing that we'll see is an integral with respect to z. Here we'll see an integral with respect to z first. Here an integral with respect to y, an integral with respect to y, an integral with respect to x, an integral with respect to x. And after you do this interior or innermost integral, you have now a second integral with respect to y, a second integral with respect to x, a second integral with respect to z, second integral with respect to x, a second integral with respect to y, and a second integral with respect to z. And then whatever you get, you integrate with respect to x, y, x, z, z, or y. And so you just have to start finding the bounds in each appropriate case. So for example, here you have to find the bounds for z. The point is that z goes between 0 and 3. So you would put 0, 3 here. In the middle you put the bounds for y, which are 0 and 2. And for x you put 0, 1. And now if you notice the difference between this and the one above is that you're fixing the innermost integral and you're just flipping the other two. So you just flip those two around. Okay? And you do something similar for on this side. So y you would put here from 0 to 2, z 0 to 3, and x is 0 to 1. And y you would put here from 0 to 2, x 0 to 1, z 0 to 3. X goes from 0 to 1, y goes from 0 to 2, z goes from 0 to 3, and finally x goes from 0 to 1, z goes from 0 to 3, and y goes from 0 to 2. And then we just compute them. And we compute them using the same principle. So I'll just do the first one and the last one, and you'll see that it will give us the same answer. Hopefully I'll have enough room to do it in just one chalkboard. But let's try to do this one first. So 0, 1, 0, 2, 0, 3, x, y, and z, dz, dy, dx. Again, what this means is integrate first with respect to z. That means that x and y are constants. So you get 0, 1, 0, 2, x, y, c squared over 2. That's going to be evaluated from 0 to 3, dy, dx. And again, at 0, nothing happens. At 3, you get 3 squared, which is 9, so you get 9 halves. That's a number, you can pull it out of the integral if you like. So it seems we'll have to continue here, but that's fine. So now you integrate with respect to y. Remember that. So x is now like a constant. And y is being evaluated at 0 and 2. So again, at 0 you don't get anything. At 2 you get 4 over 2, which is 2. So the 2, well, it will be 9/2 times 2 times the integral from 0 to 1 of x dx. And this one, well, is x squared over 2. So you get 9/2 times 2, x squared over 2 from 0 to 1, right? That's 1/2. And so the answer is 9/2. Okay? And so now we'll do the same, but with the last one. And if you want to practice, you can try the other possibilities. Let me just copy this before I forget it. So I want to do 0, 2, 0, 3, 0, 1, x, y, z, dx, dz, dy. So, okay, this is a nice order of integration because it's pretty different from the one we had before, so you can actually realize that it is not the same integral that we are doing. So in this context, we're integrating first with respect to x. So we get the integral from 0 to 2, 0, 3. So now with respect to x, it means that y, z are constants. So you get y, z, x squared over 2. X is being evaluated at 0, 1. And then dz, dy. And again, this is just 1/2. So you pull out the 1/2. So you get 1/2, 0, 2, 0, 3, y, z, dz, dy. And again, now we're integrating first with respect to z. So y is like a constant, so you get 1/2, 0, 2, y is a constant, so you get y, z squared over 2. This is being evaluated at 0 and 3. And whatever you get, you will integrate with respect to y. And so again, this gives you 9/2, so you get, 9/2 times 1/2 times 0, 2, y dy. That's y squared over 2. So this is 9/4 times y squared over 2 from 0 to 2. And again, this is 4 over 2, that's 2. And so you get 9/2. And the point is that had you done this in the other 4 different ways, you would also have obtained 9/2. So what we will do in the next video is study situations where the regions of integration are not just rectangles, but they're like more curvilinear things.